This actually is the last year that Math 115 is going to be taught. We're going to be committed to switching over to a 4-hour 111. Oh, I should explain. Sorry. Math 111 and 112 are 3 contact hours a week. They're always, from now on, they're going to be taught in 3 50-minute sections. So 3 contact hours, 3 hours of credit. 115, 116, 3 lecture hours, 1 lab hour. The lab is like a recitation or problem session, a place where you go to do extra work, review material, group work, quizzes, that kind of stuff. 4-hour courses, 4 hours of contact, 4 hours of credit. From next year on, we hope that we will be changing 111 into a 4-hour course because we believe that people really can use the 4th hour. Extra review, more time to get through the syllabus, a more leisurely pace, things aren't as hectic. So if you're going to be doing your math requirement this year and you want to study biology or NDB, then 115, 116 will be your choice. If you're going to put your math off, which we don't typically do, although it's math 116, if you've got a good Calculus 1 course, then you are well prepared for Math 116 in the fall. And the nice thing is, you take that course and now you've fulfilled the biology math requirement or the NDB math requirement, except for QTM. The Math 116 course also contains something different. This is sort of the life science Calculus 2. It's not just calculus. At least a third of the course, maybe a little bit more, is probability theory. So you learn about chance, you learn about the basics of probability and conditional probability. We show how probability is applied in areas like genetics. So the 116 course really is the right course for somebody who's interested in biology. So anyway, again, all of this advice is printed, and there are all of these options. And whenever you give choice, things become more complicated because they're Now, I've also put in this package just examples of syllabi from previous years. These aren't intended to scare you. This is just how a course is described. I should say, most people use... Have you been introduced to Blackboard?
Mm-hmm. Yeah.
Uh-huh. So, we use Blackboard to, it's a good, oh, sorry. In many ways it's awful soft. But it's a good way to organize a course. So, okay, so from last spring, it's probably all these classes are the same. It's still not the course. Now let us. That's okay. So, for instance, exams. We'll post review materials, a syllabus, and then eventually a copy of the exam and key. So this is available for you to prepare for the exam and to go over after you've got your graded exam back. There are lots of supporting materials that are posted. So if there are readings that we'd like you to do, then we'll post them here. And then there's Grade Center, so that's a place where you can keep track of how you're doing in class. And this is one of the things that's okay, so we won't wait for it. Does anybody want to ask any questions about which course to take, or if you're well prepared? Yeah.
If you're not very strong in math and you did not take a good pre-calculus class in high school, what class would you recommend?
So when you say you didn't take a good pre-calculus class, did you take a pre-calculus class?
I took a trigonometry class.
Okay. And you did algebra 2?
Yes.
And how did you feel about the trig class?
I did well in the class, but I did not feel like I mastered the material.
About the only option that you have is to do Math 111, Calculus 1.
Okay.
This year you could do Math 115. That would be reasonable. Or if you decide to put the math off, you could do that. If you're really concerned and you're afraid that a university math course, a calculus class would be a disaster, we don't have a pre-calculus offering this year. So what you would have to do is wait and pick up a pre-calculus class over the summer. Or, if you think you're disciplined enough, then you can use a resource like Alex to improve your pre-calc background. And the nice thing about Alex is it tests, it's class testing. So that, one of those two things you have to do. Well, I guess there's three. You could take a calculus class, yeah.
Is it like, when you're on your pace for calculus, if you take like Cal 1, do you have to automatically take Cal 2? Or like, is it like, are you talking about you go from Cal 1 to, 115?
We're not recommending that people take Math 111 and Math 115. There's too much repetition in the material. The classes are really quite similar now. Like I say, if you're very worried about your pre-calculus background, it would be better to do that kind of a class. If you've got good pre-calculus background and you want to do biology, take Math 115 this fall. If you're not sure about what major you would pursue, and maybe you want to go to the business school or something like that, then Math 111.
No, I want to do like the MBB, but then I want to like kind of exempt out of Cal 1. So.
Have you got AP credit?
Yeah, I got 5.
Oh, take Math 116 this fall. Be one of the inaugural group taking it in the fall. So really, we are charming here.
If I took stat in high school and I didn't do amazing on the AP exam, should I take the I think you called it the QTM 100?
I think you have to.
Yeah.
Yeah.
Okay.
Yeah. Now, I don't know how AP statistics credit affects the QTM requirement.
I think it's a requirement no matter what.
Yeah.
It would
Okay.
help you with QTM 100, so you could get that A,
Yeah.
but I don't think you can exempt out of QTM 100.
Oh,
I don't think so. I think that they're really requiring it, and part of it is because I don't think that AP stat courses typically teach R, which is
No.
one of
Yeah,
the things
no.
that they want people to come up with. Yeah.
I took AB Calc, and I felt really secure in it, except for related rates. Anyway, so I wanted to know, would it be recommended, do you think, if I went ahead and took 116 or Calc 2, or is related rates within Calc 1?
Related rates is part of Calculus 1.
Okay.
It's really de-emphasized in Math 115. You could certainly take Math 116 without having a great deal of confidence in related rates.
Okay.
That wouldn't be a problem.
Okay.
And believe me, this is a deficiency that's easy to fix. It's related rates cause people a problem because it's usually rushed and it's not explained why you're doing it or really how it's working. It's the chain rule dressed up in word problems. So it can be, yeah,
Thank you.
but it's. So I was going to talk a little bit about what is, yep.
Okay, I don't understand what QTM is. Like, how is that different from regular calculus?
No, it's a statistics class. quantitative, I don't know.
Theory and methods. Yeah, quantitative theory methods.
Okay, is it a requirement for like the biology major?
Biology requires QTM 100 as of fall 2014. NBB has required it for several years. You have to take it.
No, you guys don't have to. I have it because you're old. But it is applied statistics, so it's actually useful and fun. I mean, it's fun.
Well, this is better than mean, median, mode.
Yeah.
How do you get to Calc 1? So you have to take Math 115, 116, and then the next year you take Calc 1?
No. It's one or the other. 115, 116 is Calc 1 and 2 for biology.
Oh, okay.
111, 112 is Calc 1 and Calc 2 for economics, math, physics. They're separate from each other. After this year, there will only be, now I knew I was warned. On and after fall 2015, now it's been suggested that we should renumber this, but Calculus 1 followed by either Calculus 2 for biology or Calculus 2 for physics and economics, or Calculus 2 for biology. Business school. That's after this year. This year you have the option that this first one should be this. That's the bio track. That's the standard track. So this is 2014. Get my coordination back soon. 2014.
But can we still use the top method when we go in?
When are you going to use it? This year?
So like when we go into the fall? Like
Yeah, here's what you're going to do is this instead.
Yeah.
Yes, definitely.
116.
Or you could do that.
Either way.
Either or. There you go.
Either way. Yeah.
So if you do NBB or bio, do you have to do 115 or 116 and 116, or is it recommended?
Okay. Biology requires 116, the second course. NBB has a requirement that reads 115 or 116. Which doesn't make sense, but the intention is that if you have strong math background, you should challenge yourself to do 116 and acquire the material there. If your background isn't so strong, if you're interested in less quantitative things, if you're more on the psych side of things or the anthro side, 150s. It's kind of.
Okay, I didn't take a statistics class, but I took a calculus class. Will I be okay for the QTM?
Yes, there's no prerequisite.
Okay.
No.
Wait.
In the back, again?
I know that the math, the 116 is more of like a science kind of math, but what if you don't have a strong science?
Oh, I never took biology, ever. I teach it. No problem. The applications, so when we, for instance, when we start to apply probability to genetics, and I say things like Punnett square, there's a lot of nodding, and people are comfortable with this picture. And that's nice, but none of it is required with respect. No familiarity with any particular science. Now, there is some sophistication assumed. So when we talk about rates of change and we apply it, there are units. And so if we're talking about velocity, we're talking about meters per second, and acceleration is meters per second squared. And I know now that when you talk about temperature in Kelvin, you don't get to say degrees. They're little things. Did you know that? There's degrees centigrade and degrees Fahrenheit, but in Kelvin, it's just Kelvin. No, you don't know specific knowledge.
Another question?
Yeah.
Okay, this is about the QTM again. I'm just trying to figure out what's going on. Okay, you said there's no prerequisite for that class.
Right.
So can I take it this fall, or should I wait?
You can get in.
Oh.
You can get in. Yeah. I don't know if they save spaces for freshmen.
Okay.
There's a lot of demand for the class. I mean, of course, there will be space at some point, because it's a required class.
At some point, spring, probably.
Now can I, yeah?
So, sorry,
No.
building off. If you take 116 in the fall semester, then you would more than likely be able to take QTM and.
Yeah.
That's it.
And it would actually be nice because we do more probability theory in 116 than is in QTM 100, so you'd really be well prepared.
Okay, thank you.
Now, I was going to give an illustration of how math can be different in a university class as opposed to a high school class. One thing that you might find quite surprising is that calculator use is very rare. Almost no calculator use allowed. The only time we use calculators in 115, 116 is when we're doing statistics. And we don't do much of that anymore, so, and except for a few applied areas, you'd be expected to do basic calculations. And if you've always relied on the calculator, that can be a little bit surprising. But it's true. Computer use, you're going to go in, you're going to be told there are no laptops here. Because they're really not used in the class proper. You use them afterward, but in the class your attention's on blackboard or on the screen, whatever is being done. My rule about food is it can't, oh no, you can keep it over now. My rule about food is that it can't make noise and it can't smell. This is supposed to be another joke. It's really quite upsetting if you walk into class and, got a very,
Sandwich. Yeah.
well, or eggs and bacon, for instance. The person next to you is vegan. But you'll find that your days are going to be quite busy, so you may be wanting to eat in class. It's just really was supposed to be enjoyed. I want to get a little more serious for a moment. There's an interesting book on kind of the nature of mathematics. Now, this won't be a topic in the class, but I just wanted to point out how a math professor thinks about what he or she is trying to do in a class. And something that may be a surprise, it depends on the kinds of teachers you've had. Getting the right answer isn't the only goal. So demonstrating reasoning and supplying the steps and showing how you arrived at a conclusion is as important as getting the right answer, which it can be a different way of thinking about it. So here he's talking about the fact that a good math teacher should be a guide to good reasoning, and a math course that fails to supply this is essentially teaching the student to be a very slow, buggy version of Microsoft Excel. Well, if you've used Excel, this is quite an insulting statement. that clear thinking, being able to formulate a solution that involves a number of steps, and communicating that is an important part of what we do in a math class. Anyway, it's actually a fairly interesting interview. But he goes on to say that it's not the case that being able to compute basic arithmetic is unimportant, but it's one of those things that we should be able to take for granted. And you know yourself that there's a lot of variety in people and their ability to follow a calculation quickly. Some people just see things easily, other people struggle to follow manipulations and deductions when there's a lot of symbols. So one thing that you're going to probably experience in university math class is that some of this stuff happens fairly quickly up on the board, and not everybody is a gifted expositor or necessarily sensitive to the steps that cause difficulties. In fact, it's necessary and it's better for you to take that stuff away from the lecture and work through it on your own or with a group of friends. In fact, having a study group in a math class can be a very useful thing. It's very common in the lab sciences. It's a natural thing to have happen because you're going through these labs as well as the lectures together. But it's also helpful in that. There's something else that he goes on to point out. I think one of the things is math teaches the significance of skepticism. So here's this very simple example. The example I give in the book, so I'm reading right, is that you're working a word problem that asks you to compute how much mass of water there's left in a jug, and you get an answer of -4. So this has probably happened to you. You've done a calculation and it's ridiculous. Do you continue? Or do you say, gee, -4, that's just not reasonable? Or you're doing a calculation in probability theory, and you come up with a probability of 2.6. And you know, percentage-wise, 2.6 is okay, but probabilistically speaking, probabilities are always between 0 and 1. So there are little things that you are attentive to when you're doing math. But there's one other thing that I wanted to show, because I thought this was neat. I'm going to give the answer away. You can read this. You have a rare disease like brain cancer, and you look at the rate of incidence in different states, there are very big differences. There. Okay, now, I don't know if you've seen this before. If you have, don't give the answer. But when you look at the numbers, they're rather strange, because at the very top of the list you see South Dakota with an extremely elevated rate of brain cancer. If you look at the bottom, you see North Dakota with almost none. So that's very strange, because North Dakota and South Dakota are not actually all that different. And don't tell that to somebody from North Dakota or South Dakota, but you see his point. So he continues. When you look at the numbers a little more closely, you notice that the states at the top of the list, South Dakota, Nebraska, Alaska, Delaware, Maine, and the states at the bottom of the list, Wyoming, Vermont, North Dakota, Hawaii, District of Columbia, have something in common, which is that they are very, what should they have in common? Geographically, they're diverse. Size-wise, Alaska is the biggest. Delaware is pretty tiny. Hawaii is probably tinier. District of Columbia, I guess, is smaller still, physically. But what did the states have in common that could lead to some of them being at the top of the brain cancer statistics and some of them being at the bottom of the brain cancer statistics?
If
that's in fact the kind of issue that comes up in statistics all the time. How did you get the numbers? But for purposes of this discussion, let's assume that this data is all arrived at with a common method. But that's in fact a very good point. The skepticism about where did these numbers come from? How were they arrived at? Now this is something simpler. I read it too fast. I didn't get a chance to think about it myself. And that's, all of these states have very, very small populations. And when populations are very small, statistical conclusions become more suspect. It can just happen by chance. If you've got a relatively rare form of brain cancer, and it's just by chance that in South Dakota, you get an extra handful of cases, then that can skew the statistics, but that would have no impact in California. And he's just using this as an illustration of, in fact, this is statistical thinking, is that these kinds of issues will become something that after you do 116, you do QT 100, you'll see this repeatedly and you'll become quite used to thinking about these kinds of things. So really what I'm trying to point out is that we do some interesting things, and thinking is really an integral part of doing math. Now, I was going to do a couple of topics from the Math 116, 116 syllabus. How many of you taken? How many of you have taken a calculus class? Oh, that ruins it. Thanks. I was going to go through and illustrate where the idea of instantaneous velocity comes from and the importance of limits. But since you've all taken, almost all taken a calculus class, this will not be very surprising. So, but I'll just humor me for a couple of minutes, and I'll just remind you about it. So we have a maybe this is a predator, and this is a food source, and this is a straight line. And the predator is approaching the food source, and you'd like to get an idea about the velocity. At a time. So I've suppressed the word instantaneous. So the predator starts at some position. Maybe this is meters. Maybe this is a very slow predator. I'm not sure how this is going to work out. But there he is at position at position 25, and he's going toward the food source at 0. And suppose you can measure position, but not velocity. But you want to at least approximate approximate velocity at any time, some. Say t equals 5 seconds. What could you do to get an approximation of the velocity at some instant? So at time 10 seconds, at time 0 seconds, say the predator's here, at time 10 seconds, it's maybe got to the food source or the prey. And at any instant, you can measure the position on the axis, but you can't measure the velocity. How could you at least approximate the velocity at a given time?
You can use the position equation and put in 5 for any variable t.
So by the position equation, I didn't give you a function to describe the position. I'll do that in a minute when we want to get more ambitious. All I can do is tell you, you tell me a time and I'll tell you where it is. The position is. So, yeah,
Velocity was distance over time.
so average velocity in a time interval, say from, let's go 1 second below to 1 second above, just to pick a number. You would have, and maybe I'll use x is position at time t. So the average velocity is the position at time 6 minus the position at time 4 over 6 minus 4. Just what you said, this is the change in position. I haven't written on a board for several months and change in time. Forget how to write. So, right?
Yes.
Now, whoever you just told this to says, I would like a better approximation. This predator is moving at wildly differing velocities. I'm not impressed by this average. I want a better approximation. What could you do?
You can,
Decimal.
you can do the
Both same things. Decimal interval smaller. Average velocity, and this doesn't have to be balanced that evenly about 5, but just make the interval smaller. If you make the interval smaller, you're still computing an average velocity, but it's likely that it's a better approximation to the instantaneous velocity than the larger one is. Just because even if it's varying fairly wildly in its speed, it's still going to be less variability here than there is here. Right? So it's a better approximation. Now, do you remember what happened in your calculus class? A miracle occurs now, and you do something and instantaneous velocity emerges. Do you remember how it happened? Before you can take the derivative, you have to define the derivative. Arrays of numbers, you use them to describe, well, systems of differential equations, which is like this is a system. And then applications for life science models that we'll develop, epidemics, predator-prey, competition, the neuron, and then probability in its applications.
What is the pace of the calculus class? Like, how many topics would you cover in class?
Usually these books are set up so that it's like a section a day.
Okay.
And
So on an exam, how many chapters would that usually be?
well, Math 111 is typically 3 in-class tests and a final. And math 115, 116 is usually 2 in-class tests and final, and then quizzes. There's almost never is homework given for credit, because there are all these tools out there you can use to solve problems, like Wolfram Alpha and various things like that, that make it really impossible to get homework. So almost everybody gives regular quizzes, and they count some small percentage of your grade. How the grades are broken down varies from instructor to instructor. I typically have something like 35 to 40% on the final, and the 2 midterm exams together 40, 45% in the quiz. So the exams in 111 in particular, they're only going to cover a fairly small amount of material. But then the exam at the end, the final, is a cumulative exam. Yeah.
Could we discuss our reading assignment on conditional probability?
Oh, yeah. Who gave which one? I did?
Yeah. Medical false positives.
Okay. I wanted to talk about this. So here we go. So this is a very common illustration of something called conditional probability. It's usually set up along the following lines. You have a population with a known rate of some rare disease. Now, how it's known is an issue, but population with a known proportion of diseased individuals. Maybe this is something just like it may just be a mutation at a certain location on the gene, so maybe this is not unreasonable. Or it could be some nasty, deadly disease. And so I'll make up a number. I'll say the proportion is, so the numbers I make up are green. 0.01. Say. Now we have a test. There's a test for the disease. It's not a perfect test. It makes mistakes. It makes mistakes of 2 kinds. First I'll tell you the terminology, then describe what these mean. Its sensitivity is 0.94, and its specificity is 0.95. So what do these proportions mean? This means that the probability of a positive test, given the presence of the disease, positive means it's there, not, so given disease, is 0.94. And if the word probability bothers you, just think of it as you give the test over and over and over and over and over again to a diseased group, and 94% of the time it comes back positive, and 6% of the time it comes back negative. So that's the sensitivity, 0.94. Also, tied to this, the rate of false negatives is 0.06. Specificity is the probability of a negative test, given that the disease is not present. So, this is what happens when we don't practice. The proportion of false positives is 0.06. The proportion of false, false negatives.
There you go.
Now, these things add up the way they do because you have a diseased person, either you're gonna get a positive test or a negative test. So the two things are gonna add up to 1, 0.94, 0.06, 0.95. If you have somebody who's not diseased, you're gonna get the correct negative, or you're gonna get a false positive. Anyway, this is just terminology. Now, here's the question. What is the probability of having the disease given a positive test? Because if I go in, get tested, it comes back positive, what's the probability I'm actually diseased? This is, once you learn what it is, this is a conditional probability. This is the probability of having the disease, D, represented by D, given, that's what the bar stands for, a positive test. Now, the way this probability is understood, in fact, the way it's defined is, this is the proportion of those testing positive, which are diseased. So it's a fraction, and here you can put down proportions, or you can put down numbers. You have to use the same thing. But, so this could be the proportion of positive tests divided into proportion of positive tests and disease. That's actually a definition. That's the definition of conditional probability. So what are my odds of being diseased given that the test has come back positive? So you want to compute this. Now, this isn't something that you have to. Should I do it? I'll show you how to reason with something called a tree or a multiplication tree. You may have seen this. We have two stages. We have the disease state and the test result. And either you're diseased or you're not diseased. And labels go on the edges of the tree corresponding to the probabilities. So this is 0.01 and this is 0.99. Now, in both cases, you could come back with a positive test or a negative test. A positive test or a negative test. And now we put probabilities down corresponding to the specificities and specificity and sensitivity. The probability of a positive test given the disease, what should I put on this edge? And on its complementary edge? No, 0.05. And now, here comes the magic. The magic of probability. The probability of positive and diseased is the product of these two. It's right from here. Yeah, but you have to kind of unwind it. Whatever. So 0.94 times 0.01, which is some number. The probability of negative and diseased, 0.06 times 0.01. The probability of positive and not diseased, and this notation stinks. I mean, you would have much better symbolism if we were doing this carefully. I'm just sort of, is a 0.05 times 0.99. And the probability of negative and not diseased is 0.95. Now, we can calculate now how worried we should be. Right? Because the numerator is the probability, it's the proportion, but if I use probabilities in both places, that'll be okay too. Proportions and probabilities are the same thing for this. This numerator is what? Probability of positive and diseased. Do we see it? Mm-hmm. Probability of positive and diseased. Numerator. Now, what's the denominator? All the positives. So how do you get positive here?
The top one and the third one, and you add them together.
Yes. You've just committed, you've just stated what's called Bayes' theorem. Now, this number is, I'd say, 15%, 0.15 maybe. If you calculate it, I don't For this part, you use calculators. Yeah. Less than a fifth, well under a fifth. So only a fifth of the time will the positive test be accurate. Now, there's two ways to look at that. Hey, 15%, 16%, great. On the other hand, this is 16 times higher So this rare disease example is supposed to indicate how conditional probability can really sharpen your intuition. And there's all kinds of stuff. You can Google this and you get all kinds of commentaries on this. And a distressing thing is how badly doctors do with this kind of reasoning. This is something that apparently comes up all the time. Your intuition stinks when it comes to this sort of thing. Which is, I shouldn't point fingers at doctors. Almost everyone's intuition will stink if they haven't gone through this kind of an example. Now, there's a twist to the handout. So this is as I say, you do this on the second day of probability theory. This isn't complicated, but you would like to have some notation and have developed the basics, have a good explanation as to why this conditional probability definition makes sense, how these multiplication trees work, what's going on. So that takes a couple of days. But there's an issue. And it's pointed out in the reading. It's under this subsection, Houston, we have a problem. And there's an assumption here about what the .01 applies to. And for this calculation to give the conclusion we're reporting appears, it's not just that the disease proportion in the population overall should be .01. It's that the diseased proportion in the population tested should be .01. And again, this is something that almost none of the treatments I've seen in textbooks mentions. It's an unstated assumption. The assumption is that by and large the proportion of those tested follows the proportion of infected. The proportion of diseased in the total population and the proportion of disease in the tested group, those two things are about the same. Now that makes sense for a lot of diseases, but doesn't make sense if the test is only given to individuals who have a bunch of symptoms or a history or something that indicates a proclivity toward the disease. Then the two numbers are much different because the proportion of disease among the tested group would be quite a bit higher. So this is something of clinical significance. Now, one thing that occurred to me the first time I read this stuff is, how do you know, how does one guess at the sensitivity and specificity of a test, of a medical test? Where would that come from, that knowledge? How could you know that for diseased individuals, positive tests show up 94% of the time, and false negatives show up 6% of the time?
You need to give the test to like a group of people.
You know we're sick. Right. So that's the answer. That is an answer to sensitivity. Either you have a foolproof test to which you can compare the results of this test that you're using, or you've got a diseased group that this is a diseased group and none of your own testing. There. That's a way to discover sensitivity. How do you discover specificity? And if you tried to do the analogous thing, you would be asserting that you have your hands on a non-diseased group. That's what the test's for. Maybe you could figure that out from some other direction. You're guaranteed not to be diseased. I guess maybe you could give the test, record the results, and then watch the group. see who dies and who doesn't. And work backwards, figure out. It's cruel. Hey, a lot of medical research is done in just this way. But these are not trivial considerations, sensitivity and specificity. So is that your question? Well, thanks for listening. It's one of the topics that's fun to teach in class. I mean, it is a real life application of probability. Okay, so what do you have?